The broadcast is now starting. All attendees are in listen-only mode.
And a failure analysis must include a stress criterion and a failure criterion. So a failure analysis definitely must include a stress analysis and a failure criterion. So what do we mean by this? So we do the ANSYS simulations here. We do the stress analysis over here. And then we need a failure criterion. It's good that, we have an ANSYS simulation, but we get a lot of numbers out of ANSYS, but what do they mean? So we need the failure criterion to convert all these numbers to something meaningful that as engineers we can use and we can determine failure. So fracture mechanics parameters in ANSYS is, we have the J integral. ANSYS can give you J integral. ANSYS will also output energy release rate and of course stress intensity factor. And lately, in the latest couple of versions of ANSYS, like 16 and 17, T-stress, material force, and C-star integral are also outputs that you can get from ANSYS. Now, what are these factors here? The J integral can be defined as a path-independent line that measures the strength of the singular stresses and strains near a crack tip. If this is our crack tip, right at the crack tip, the stresses are singular. Of course, if you run ANSYS, ANSYS is not going to give you an infinite number. It will give you a finite number. But as you increase the mesh density near the crack tip, the stress will go up and up and up. So it is theoretically infinite. But if you take an integral in a anti-clockwise manner, this line integral will give you a number, basically. You're basically integrating around the singularity here. And this is called the J integral. You integrate it and you will get a number. And the other important thing here is that this is a path-independent line integral. What that means is that you can start from here and end here, or you can take a larger integral path, or you can take a smaller integral path. Theoretically, they should all give the same answer. Now, what may happen is that numerically, you may get slightly different answers due to the numerics of the finite element analysis, but in theory, you should get the same answer from any integral. The next one that ANSYS outputs is the energy release rate. The energy release rate can be calculated from the stress intensity factors, K1, K2, K3. And K1 is the stress intensity factor for mode 1, K2 mode 2, and K3 mode 3. So ANSYS already calculates stress intensity factors K1, K2, K3, and you can take all of them into account to come up with one failure criterion, which is the energy release rate G. And stress intensity factors are, again, they're automatically calculated by ANSYS, and it can be K1 is for what we call mode 1 loading. Mode 1 loading is where the load is perpendicular to the crack, and there's mode 2 loading where the load is in a shear mode, it is parallel to the crack, and mode 3 loading is when the loading is out of plane shear. So T-stress, this is the stress acting parallel to the crack faces. Unlike J integral, it can have both negative and positive values. Positive T-stress values promote fracture, whereas negative T-stress values results in larger plastic zones. And material force is another one that's output. Material force method provides parameters for global material and dissipation forces that yield near tip crack driving force. Can be applied to all kinds of material models like elastic, viscoelastic, plastic models. And finally, C-star integral creep crack growth becomes concerned when structural components are operated at high temperatures, like nuclear industry or solder joints. So the C-star integral can be used to evaluate crack tip fields under creep deformation. C-star integral is a path-independent integral, which is the steady-state creep analog of J integral. So this is a summary table. It shows which parameters is applicable for which assumptions. So the J integral is mostly used for linear isotropic elasticity or isotropic plasticity. Energy release rate can be used for linear isotropic elasticity, orthotropic elasticity, or anisotropic elasticity. Stress intensity factor, very important, is applicable only for linear isotropic elasticity. T-stress is good for linear isotropic elasticity as well as isotropic plasticity, similar to J integral. Material force is applicable for nonlinear materials, including plasticity, viscoelasticity. C-star integral is good for creep material behavior. So if you're just doing creep, then you may want to look into C-star integral. If you're using any plasticity, you can look into T-stress or J integral or material force. For orthotropic elasticity, definitely energy release rate and stress intensity factor can only be used for linear isotropic elasticity. So for crack growth simulations, ANSYS also offers 3 different methods: VCCT-based interface element method, cohesive zone method, and XFAM-based methods. Those are the 3 different methods that are available. And I have to say, cohesive zone method is available in Workbench. XFAM is available in ANSYS Classic. That is mechanical APDL. So let's see how we can do crack propagation. This is an edge crack plate analysis. There's an edge crack, as you see here, and this is aligned at a certain angle beta, and there's a stress applied, and the question is, when this crack starts running, which way is it going to run? And this can be solved both using fracture mechanics tools and cohesive zone elements in ANSYS. And so here is the animation. So fracture parameters can be calculated using kcalc on CINT commands in ANSYS APDL. And you can do the same problem in the Workbench as well. Crack initiation angle and energy release rate can be calculated from stress intensity factors. And cracks propagate straight, parallel, normal to the loading direction. Not parallel, normal to the load direction. So interface modeling is also here. We are looking at an initial crack in a thin film where we have an interface in different materials. Here there's an elastic substrate, as you see here, and there are different materials. So there's the thin film, interface material, and an elastic substrate. So here, an edge crack propagation in a thin film substrate, silicon dioxide and silicon is studied. Effect of interface layer uncracked propagation path is examined using cohesive zone elements. Here you can see the propagation. So the crack starts over here. It's a silicon dioxide. So that's the propagation in silicon dioxide. And then there's an interface here. So crack propagation is performed quasi-statically. Fracture parameters are calculated at each propagation step, and the geometry is updated for the next propagation step. Cohesive zone elements are placed between thin film and substrate to model the interface. So, crack growth simulation using cohesive zone elements. The interface surfaces of the materials can be represented by a special set of interface elements. So in ANSYS workbench, wherever you have these contact elements, you can convert them to these interface elements, and that you can convert them to these cohesive zone models, and you can use the cohesive zone material models for these interface elements. So the concept of these cohesive zone materials was established to study perfectly brittle materials and adapted to ductile fracture. So fracture simulations using CZM require experience in order to determine input parameters such as mesh size and properties to characterize traction separation laws. So the interface elements are for modeling interface delamination at the interface of two materials. The elements are capable of representing the cohesive zone between the interface and can account for the separation across the interface. So this would be excellent for modeling the crack propagation right at the interface between the solder joint and the copper pad. Interface delamination with contact elements is referred to as debonding. Debonding is modeled with contact elements which are bonded and have a cohesive zone material model defined. What that means is in ANSYS workbench, if you have specified contact elements at the interface between the solder joint and the copper pad, you can convert these contact elements and use them as interface elements and associate with them a CZM model, a material model. So debonding is a special form of delamination. There are several advantages to using debonding to model interface delamination. Existing models with contact definitions can be easily modified to include debonding. And standard contact and debonding can be simulated with the same contact definitions. Therefore, crack propagation between solder and pad can be simulated using cohesive zone interface elements. So cohesive zone interface elements, where you take the contact elements that are automatically defined in ANSYS mechanical and you convert them into contact debonding. So that's the fracture mechanics part. So with respect to fatigue, the question is, can classical fatigue be used for solder joint reliability? And when it comes to fatigue, there's stress life fatigue and there's also strain life fatigue. So stress life fatigue is represented by an ascent curve. What does that mean? The vertical axis is the alternating stress, and the x-axis is the number of cycles to failure. So each point here represents a fatigue failure. What does that mean? A fatigue failure means when cracks develop that can be seen visually, then each one of these is that point. So this is like, you can think of this as stress-life fatigue curves as crack initiation. So when cracks initiate and reach a visible crack length, which is of the order of 10,000ths of an inch, then we can say that is A0. That is the initial crack length when the cracks initiated. So stress-life fatigue may be used in conjunction with fracture mechanics, where these data points can be the initiation stage, crack initiation, the initial crack length. Then, the crack propagation can take it over from here. So in stress life, in ANSYS Workbench, you can actually do these fatigue calculations, and fatigue calculations can give you again the A0, the crack initiation, initial crack size of say 1,000th of an inch. So low cycle fatigue is also determined by the strain life fatigue curves. Strain life fatigue curves are replaced, in the case of strain life fatigue curves, the vertical axis is the strain amplitude. If you note in the stress life fatigue curves, the vertical axis was the alternating stress. So instead of alternating stress, we are plotting strain amplitude here on the vertical axis, and on the x-axis, number of cycles to failure is plotted here. So basically the strain can be represented by two asymptotes, this red asymptote and then the blue asymptote. The blue one is the elastic, what we call the elastic component. The red one is the plastic component. So the blue segment is the elastic portion. It's called the Baskin equation. And the red segment is known as the Manson-Coffin equation. The red segment is the Manson-Coffin equation, where there's a lot of plasticity. So the total strain amplitude is the combination of both, and that is the green curve here. So the Baskin equations for elastic strain amplitude can be written in this form here, and the Manson-Coffin equation for plastic strain amplitude can be written here. So if you add these two together, you get the total strain life. So the Coffin-Manson equations for low cycle fatigue model is one of the most often utilized models in the electronics industry for life prediction of solder joints. IBM has used this simple formula for a long number of years, where life is really related to 1 over gamma squared, where gamma is the plastic strain range. The above equation is valid for plastic strain. However, solders are prone to creep deformation, especially at operating temperatures. Therefore, CM equation need to be modified to account for creep, which causes voids and cracks at grain boundaries. So this modified Coffin-Manson has been successfully used in solder joint reliability. So then the question becomes, how do I model the material behavior? Do I use creep modeling or do I use viscoplasticity? What is the difference? So creep is a rate-dependent material nonlinearity in which the material continues to deform under a constant load, whereas viscoplasticity is a time-dependent plasticity phenomenon. The plastic strains are dependent on the rate of loading. So viscoplasticity is the main topic here, and creep is a subtopic under viscoplasticity. Here we are looking at on the vertical axis the force and on the x-axis time for the case where you apply a displacement to a structure, and if that structure creeps, the force in the structure starts out initially at a high value, and over time it starts decreasing under constant applied displacement. So creep strains are plotted usually in this manner here. The vertical axis is strain and the x-axis is time. There's a primary component, there's a secondary component, and there's a tertiary, the third stage. So we don't model anything here. We assume as the strain reaches this point here, things have failed. But we do model primary and secondary regions. So creep is the deformation of material over time in such a way that some of the stress is relieved. Creep strain rate is a function of time, stress, strain, temperature, and neutron flux level. Sometimes stress relaxation is used instead of creep. The material is assumed to be isotropic. And ANSYS provides 4 options to model creep: primary creep, secondary creep, and there's actually primary plus secondary creep, irradiation, and user-defined models. Viscoplasticity, on the other hand, is characterized by irreversible straining that occurs in a material over time. The plastic strains are assumed to develop as a function of the strain rate. And ANSYS provides 2 options to model different types of rate-dependent material behavior. Anand or user options on the TB command can be used for this. So what are the differences in equations? There are 13 different creep formulas that are implemented in ANSYS. This is the first one, and this is the second one. Please note that these creep strains are all, derivatives of time. So creep equations are time-dependent equations, rate-dependent, in other words. And the first equation is C1, some constant, times sigma stress to some power, times strain to some power, times exponential to some power, which is a function of temperature. Whereas in the second equation, time comes into the picture instead of strain. This is for cases where time plays an important role in creep deformations. And you look at viscoplasticity formulation, this is totally different than this, except that there's also a creep formulation that is similar to this hyperbolic sine curve here. So this is the most important simple formula here. The total inelastic strain, which is the viscoplastic strain, is really addition of creep strain plus plastic strain. So where epsilon plastic is not accounted for in creep formulation. So this is the reason why you will see that there are some users out there, they don't want to use viscoplasticity, and they use a creep model with plasticity models. So, and that essentially gives them viscoplastic strain. So why don't you want to use viscoplasticity? Here's the reason why. There are 9 constants here. It's not easy to find these constants. Basically, the best thing to do is really do a Google search, and conferences like ECTC conferences is where you can obtain some of these parameters here. So that brings us to the thermal cyclic modeling for the calculation of accumulated fatigue damage, which is the DARVEAUX model. So in the DARVEAUX model, solder material was modeled as viscoplastic, and the printed circuit board as orthotropic, linear elastic, and the rest as linear elastic solids. The objective was to calculate plastic work done per unit volume. And so this plastic work done per unit volume and also per thermal cycle. That was the intent here. 3 complete thermal cycles were run. Plastic work done for the third cycle was used for crack growth. What do we mean by that? The material was cycled between 0 degrees centigrade to 100 degrees centigrade 3 times, and then the last one was used for the calculations. So DARVEAUX results show that crack initiation is only 10% of the fatigue life. So when the crack initiates at the solder joint, that you have already consumed 10% of the total fatigue life of that component. Variations in the constitutive model do not have a large effect on the calculated viscoplastic strain energy density, and the crack growth correlation is highly dependent on the element size. So this is very important. The crack growth correlation is highly dependent on the element size. So we need to use volume weighted averaging. And the crack initiation, the number of cycles to crack initiation, that is denoted by N0, is defined by this equation, C3 times delta W to the C4th power. And what is delta W here? This is the viscoplastic strain energy. And crack propagation, dA over dN, is characterized by this formula here, C5 times delta W to the C6 power. So using this approach, we can actually optimize, and this could be a multi-objective optimization where we can look at the BGA package, and this is a very generic BGA package here, and we can specify these with a bunch of parameters. And in this case here, 37 different parameters were used, where 17 of these parameters were geometric parameters and 20 of them were material properties. And this was cycled a lot more than 3 times. Why? Because we wanted to make sure that the number of the creep strain settled down to an appropriate value. So this was a multi-objective optimization. The first optimization was looking into plastic work in the upper 20% and the lower 20% of the ball. And the second optimization was looking at the difference between in the deflection between point A and point B. So this was denoted as delta max. Delta max is the relative displacement between the points A and B. So these were the results of the sensitivity analysis. So the sensitivity analysis, the vertical axis here, you can think of it as importance level. Importance in the sense that how does it affect the plastic, the amount of plastic work. Like thickness of the mold, which is the very first one here, it has a very high effect on the fatigue life, which is really directly related to the plastic work, thickness of the mold. The second one is ball pitch. So the higher the ball pitch, the higher the plastic work. And in this case, the thicker the mold thickness, then the larger the plastic work. So you can see the red ones, which are in the upper portion of the curve, they are directly related, and the blue ones are indirectly, I should say, reversely related, meaning that like the thickness of the core here, the larger the thickness of the core, actually the smaller the plastic work. So, and you can also see here, the larger the Young's modulus of the ball, then the smaller the plastic work. Young's modulus of the solder ball here. So using ANSYS, you can do this multi-objective design optimization. And so multi-objective means in the vertical axis, you plot relative displacement, and in the x-axis, you plot plastic work, and that develops a Pareto frontier, and you can actually come up with a optimized design, which is really this point over here. So that's it. This brings us to the end of our presentation.